All right. Well, good morning and happy Monday. Happy week 10. This is your last week of school, I guess of lecture, and then finals next week, and then winter break, and we'll see you next year, I guess. End of 2023, wrapping up. Anyway, let's see. Today, I wanted to show you the package stats models, module stats models. This allows you to do a little bit of traditional statistical inference in Python. So things like if you want to fit a linear regression model or a logistic regression or basically do any kind of traditional statistics, this is the package that you will want to use. We have other packages for more machine learning type stuff. So for machine learning, you would probably use scikit-learn. That's the most popular one. And then there's other packages if you want to deploy something like neural networks or something like that. But as far as traditional stats models, statistical models like linear regression, the package stats models is the package we're going to use. So we're going to go ahead and load all of these up. NumPy, Pandas, Matplotlib, Seaborn, and then the things that we are going to use is the Stats Models API and the Stats Models Formula API. The API is just basically just means how do you interact with the computer program here. Okay, so it's just what's you typing stuff into Jupyter is a form of, I guess, an API in terms of like how you interface with the computer language. So Stats Models has two forms that it allows you to kind of create commands and execute things. One is the traditional, they call it the Stats Models API, and that uses matrix form. You're going to have a matrix of predictor variables X, a matrix of predicted values Y, and that will be how the Stats Models API works. And that's it's similar to scikit-learn. Scikit-learn has input matrix X, predicted values Y, or I guess NumPy array. NumPy array X coming in, NumPy array Y of predicted values. The other is the formulas API. And this is a little bit more like R. So have you guys taken 101A in R yet? Not yet? Okay. But have you created a linear model in R where you use like Y tilde X? Okay. So if you create a linear model in R, that's more like a formula. Yes, question?
Is this posted on GitHub yet?
I believe I just pushed it to GitHub. It should be. It's under 10-1. Because of just the way files get alphabetized, 10 appears before 2. So that might be an issue. It should be. I believe it's on. It should be on GitHub. Okay. Yeah. You got it. Yeah. Okay. Great. I hope everything works. So here we're going to just do a very, very, very minimal example where my input values are X, 1, 2, 3, 4. My output values are Y, 2, 6, 4, 8. So very small data set with 4 data points. And we'll just go ahead and plot these, okay? So I've got X is NumPy array 1, 2, 3, 4, Y NumPy array 2, 6, 4, 8. I'll go ahead and make a scatter plot of this, and this is what it looks like: 1, 2, 2, 6, 3, 4, 4, 8. Using that, okay. And then here we can also make a data frame, and this is my data frame: 1, 2, 2, 4, 3, 4, 1, 2, 6, 3, 4, 4, 8. Okay. You could call Seaborn and ask for a linear model plot, and it will go ahead and try to fit a line here to the data points. And here I'm not sure how it shows its scaling. but it looks like it included some error bars as well. All right, this is how we would go about using the formulas API. I start with this because it's a little bit more perhaps familiar if you're accustomed to R's formula language when dealing with linear models here. So again, our data is stored in this data frame D, where I've got a column for X and a column for Y. And so I can say create my model using the Stats Models Formula API. And we're going to call smf.ols, and we're going to just do y tilde x. You can learn more about the different, just looking up Stats Models documentation. Here, I'll just do Stats Models over here. So this is the website for Stats Models documentation, and they've got the API and Formula API. Those are kind of your things, and then again, you can just kind of go to the reference, API reference, and look up all of these different, let's see, so time series analysis. Okay, so these are the formula class, and so you have GLS, I think general least squares, WLS for weighted least squares, OLS for ordinary least squares. So this is what we'll get, and there's not much more here, huh? And then the regular old thing. Okay, yeah. OLS, WLS, GLS, a little bit more. I think the regular API has a little bit more documentation, but you have the formula versions down here, okay? Lowercase names are aliases to the from formula method, the corresponding model class, okay? So we'll call smf.little ols. So whenever you're using formula APIs, generally it'll be lowercase versions, right? And then the full documentation. So if you want to do like lowercase ols, you can look up the full documentation for the original API, which will do capital OLS, and this will provide a little bit more explanation. And this will, but the formula version allows you to kind of take things related to I guess the formula form. So anyway, we're going to just say y tilde x, and basically the formula API will take this thing and convert it into the regular OLS API, which takes a matrix for x and a matrix for y. And so I'll show you what exactly that looks like. So, so when you do this, you get back a model, and it actually, you just have this model object, stats models linear model.ols object. And if you actually want the coefficients, so defining the model by itself doesn't do any calculations. You have to call model.fit. And when you do that, okay, that will fit the model to the data and estimate coefficients, like what is the slope and what is the intercept for ordinary least squares. Now we have the results wrapper object, regression results wrapper object. And so if you want to say, whatever you get the actual values, you can call results.summary, and it prints out pretty much almost all of our values. So you get your intercept 1.0, your x-intercept, or the slope associated with x is 1.6. So intercept of 1, a slope of 1.6. You also get related values regarding the significance of these coefficients. So here we only have 4 values here. And so my p-value for the slope is 0.2. That's also kind of this p-value for the correlation coefficient. I believe the correlation coefficient is 0.8 between these, but because our data set only has 4 points, the slope coefficient of 1.6 is not actually significant. We're saying if you just were blindfolded and you threw 4 darts at the wall, there's a 20% probability that just by random chance you end up getting something that has a slope of 1.6 and a correlation of 0.8, something like that. Okay. Now, if we threw like 10 darts, probably a lot lower probability. But here with just 4 points, we have a high p-value. You have these other things related to linear regression. So if you have already taken 101A, some of these terms will be familiar, like your AIC and BIC, Akaike information criterion, Bayesian information criterion, things like that. If you have not yet taken a course on linear regression, these terms don't mean a ton to you, and that's okay. You'll probably learn them later, but at least slope and intercept, I'm sure you guys are familiar with, and then p-values as far as is this term significant or not based on your data is there. So these are all kinds of different summary values that would be useful as far as interpreting your model, and that's what we have there. Okay, we have a warning. Omni norm test is not valid with less than 8 observations. Yeah, okay, so it's just saying you have a very small sample, and so some of these things like the omnibus, I'm not quite sure exactly how that works, goes. All right. There is something called the AB line plot, and you can take the model results object and put that in here. And when you do that, it will basically just plot the fitted line. Fitted line, here I've gone ahead and added the additional scatter points from the data frame, the X and Y, and then I've changed the limits of X and Y as well. So this will create a little plot there. Okay, let me go ahead and give you your first view quiz answer. Letter B is your first view quiz answer, question 1. All right, so that is, we have that. We can also take these same results. So these results, basically the output of stats models, whether you use the formula API or the original kind of regular linear model OLS thing, all caps thing, not the formula, you'll get kind of this results wrapper object and these different things. So you can also ask for an ANOVA table. And so you've seen ANOVA tables, I think in 101A and 101B. Again, maybe you haven't taken those classes yet. Question?
It won't let me access the view quiz. It says
Is
it's part of an unpublished module.
part of an unpublished module? All right, I gotta publish the module. Oh, you're right. It is an unpublished module. Okay. Publish module. Okay, now it should be working. Thank you.
The first answer was B.
First answer is B, yeah. All right, and so for your resulting ANOVA table, you have the source of variation, and so ANOVA can be applied to, you might have a categorical predictor, you might have a numeric predictor, where you're applying a linear model. And so if it's a numeric predictor, the one value you're estimating is your slope, and so you have 1 degree of freedom there. If you had a categorical predictor, your degrees of freedom is basically number of categories that you have -1, stuff like that. And then so you have your sum of squares from that source of variation, and then the mean squares is basically your sum of squares divided by your degrees of freedom. F ratio is your mean squares ratio between mean squares of that predicted source divided by the mean squares of the residual. So here it would be 12.8 divided by 3.6 gives me 3.555, and you use that in an F test. And again, this f-test produces a p-value of 0.2, which is not a coincidence. It's exactly the same value from the p-value for the corresponding t-test regarding whether the intercept, the slope associated, not intercept, whether the slope associated with the x variable is significant or not. But anyway, this is the ANOVA table, and again, I'm teaching this at a moment which is a little bit awkward because some of you have taken these, courses 101A, 101B, which covers linear regression in ANOVA, and then some of you have not taken it, so it's just kind of like perhaps not meaningful for some of you. But our classes in the Department of Statistics and Data Science are frequently taught in R, and I'm pushing for more stuff in Python. But right now, I'm going to just have to say, all right, well, it is possible to do this stuff in Python, and here it is. Okay, so you create your model first, and then you ask for the associated ANOVA table regarding that. Okay, and again, just like anything else, you can get more information. So under stats.ANOVA-LM, let's see. So we will look up, we want to do statistics and tool sets. And under statistics and tool sets, we want to look up there's a lot. What do we ANOVA? Okay, interactions in ANOVA. All right, this script is based on Jonathan Taylor's class notes. Okay, well, I'm not too familiar. Well, this isn't very helpful. It's just a big notebook. Not a ton of explanation here. But, all right, let's see. Okay, well, apparently there is a set of class notes that you can kind of read. So this is one of the things, the documentation, depending on the page, sometimes the documentation for stats models is really good, and then sometimes it's just kind of like some examples without a ton of explanation. So it's a little bit hit or miss as far as stats models documentation goes, but you can always kind of read up, and I think there's quite a few users of it online, so you can probably find little tutorials for each thing. For a basic thing, if you want to make a prediction for a new value, you can do results.predict. You feed it a little dictionary containing the values that you want to make predictions for, and I think you can do and so if you wanted to make a prediction for more than one value, you can put them into a little array. So I said like 2, 3, 4. And these are the different values that we would predict for these things. Now, unfortunately, they're just in an indexed sequence, so you'll have to kind of remember what exactly you were asking for. But then we have that. Okay. The traditional interface for stats models is the using kind of NumPy array notation, and this is very similar to how sklearn fits models as well. So I first covered the formula interface because that's probably most familiar to our users, but as far as stats models kind of native API, it's expecting to kind of have this NumPy array notation where you provide it a y vector or an array of y values and an array of x values here. So in our case, our x is an array with values 1, 2, 3, 4. And what we want to do is we want to have a column of ones as well if we want to fit an intercept term. So Stats Models has this function called add constant, and when you do that, now we have a two-dimensional array where x is a column of ones. It's now a 4x2 matrix. So this is my matrix X, and in beta we have a matrix beta, which will consist of basically our intercept beta 0 and our slope beta 1. And so if I multiply beta and x, okay, beta times x, each value, because I've got, basically this is a 1 and an x1, 1 and x2, basically 1 and x sub I. Our prediction is going to be beta 0 times 1 plus beta 1 times xi. And this is exactly basically our prediction for y hat sub I. And so all to say, this is basically what we're getting. Y hat sub I is going to be beta 0 plus beta 1 xi, which is just the product of our beta matrix consisting of an intercept beta 0 and a slope beta 1, where our x contains a column of ones and a column, x1, xi, x1, x2, x3, x4, and so on and so forth, and your y hats end up. So your entire matrix of y hats is beta times x there, okay? So the actual values y, though, are in this array, 2, 6, 4, and 8. And so we're going to create our model using the Stats Models API, and we're just going to say statsmodels.ols. So OLS is capitalized. All of the kind of original interface is going to be all caps in Stats Models. So when you look at kind of the different, say like linear regression things, everything's going to be capitalized with the, so if you look at statsmodels.api, basically all of your things, OLS, weighted least squares, generalized least squares, these will all be capitalized. You have like variants of these, which I'm not 100% sure what recursive least squares is. Rolling OLS and rolling weighted least squares is basically you have like a window of points, and you say I'm going to fit a model to this window of points rather than the entire data set, so it's a little bit more localized. Okay, weighted least squares says some points are more important than other points, and so you want to minimize the residuals for certain points, and then these other data points, even if we have huge residuals, it's not that big of a deal. Ordinary least square says all the points are equally valid, and we want to kind of minimize the sum of squares residuals for across all of the points. Weighted least square says these points matter. We want to minimize the sum of squares residuals for these points. These points are included in our data set, and so we'll give them some consideration, but if we have big residuals for them, it's okay. It's not that big of a deal, all right? That's weighted least squares. All right, and so so you fit the model between y and x, your matrix there. And so if you want intercept term, that has to be included in your x matrix. And one nice thing about matrix notation is you could add more predictor variables, and they just get new columns in your X matrix. Then we call fit, just like before, and then you get kind of your summary thing. And so this thing looks very, very similar, the output, just because it's almost exactly the same as basically the formula input. Really, the formula API just translates from this y tilde x, and the formula API just says, how do we translate that into StatsModel's original API, which accepts matrices here. Okay, so that's that. You have a predictor y, predicted variable y, predictor matrix x, and you just say predict y based on x, and that's the OLS thing. Is this what, 100C? You have the solution to matrix notation solution for least squares regression. And so, that solution is x transpose x inverse, x transpose y. Here we have a matrix X, and we could do the same thing. So x transpose x inverse, you have to call NumPy linear algebra dot inverse is how you take the inverse of a matrix. So I've got x transpose matrix multiplication, and NumPy uses the @ sign. So x transpose x quantity inverse multiplied by x transpose times y results in this matrix where we have a 1 and a 1.6, 1 corresponding to our intercept, basically the coefficient for the first column, and 1.6 corresponding to the coefficient for the second column being our slope. Our intercept is 1 and our slope is 1.6. Same kind of solution here, x transpose x inverse, x transpose y. Okay. All right, let me go ahead and give you your second view quiz answer, which is the letter C, okay? Okay, and for this last bit, we'll just, I'm gonna just kind of follow this example on ordinary least squares regression, and we'll just kind of walk through this. Just this uses artificial data. Okay, so so here we're going to take values from 0 to 1. Okay, 0 to 10 at intervals of 0.1. So we're going to go from 0.0, 0.1, 0.2, 0.3, 0.4, 0.5, and then we have the second column is x squared. So I got 0, 0.01, 0.04, 0.09, 0.16, 0.25. all the way up through 10, so 9.5, 9.6, 9.7, 9.8, up to 10, and 9.5 squared is 90.25, 9.9 squared is 98.01, 10 squared is 100. Okay, so that's what we have, 101 rows going from 0 to 10. Here I'm going to just add some random noise here, okay? Well, first I'm going to have an array, just 10, 5, 2. This will be the coefficients here, okay? And then I've got just some random noise here. So my X matrix, okay, I'm going to add a column for an intercept. And then we're going to multiply my X matrix times the betas, all right? So, and then the Y will be our true values plus the epsilon error here, okay? So X now has a column of 1s, still, so basically I have a column of 1s, a linear column, and then I have a squared column, quadratic. So 1, 1, 1, 1, 1, and then 0.1, 0.2, 0.3, 0.4, and then everything is squared, okay? And then as far as the true values go, it is 10 times the intercept plus 5 times the linear component, and 2 times the quadratic component, okay? So our first value is going to be 10. And then our next value, we've got 10 times the intercept, 5 times the linear component, so 0.5, and 2 times the quadratic component of 0.01, so we get 10.52. Next value, I've got 10 plus 5 times the linear component and 2 times the quadratic component, and that gives me 11.08. So that gives, that's how the true relationship between x and y. Our matrix X, we have a intercept, linear component, quadratic component, and this is what the true relationship is: 10 times the intercept, 5 times the linear component, 2 times the quadratic component. That's what beta is. Yeah, question.
So dot refers to the dot product?
Yes, dot will be a dot product there. Yep. Okay. And then, but I've created some random noise here, and so that's going to kind of cloud what the actual value is. The random noise is quite all over the place. Scale 20. So the true value is 10, but after adding random noise, I get negative 6.8. The true value is 10.5, but after adding some random noise, I get 42.26. The true value is 11.08, but after adding random noise, we're at 20.39, right? So this is kind of the problem that we have in data. There might be some true relationship, but there's also just this individual variation that right now we're just calling random noise here. Okay, so we're going to ask, fit a linear model, excuse me, between the actual values of y, which are kind of all over the place, and the prediction matrix X, okay? And we'll say create the model, fit the model, and print the results. And, one of the kind of neat things is that you get some results here, all right? And so our results are a little bit off. It says it's right now, or its best estimate for the coefficient isn't 10, but it's 16.85. Its best estimate for the linear component, remember the true value is 5, and its best guess is 2.16. And for the quadratic component, it gets it pretty good. The true value is 2, and it's guessing 2.2. So for this. As far as p-values for each of these things, it says the quadratic component is significant, the intercept is significant, the linear component, its associated p-value is currently not significant. It can't really tell it apart. But let's go ahead and take a look. It's the r-squared value using these parameter estimates is 0.92. We can also ask for the predictions. What would it have predicted? These are, we get this prediction thing. So if we want the actual values, this is what it predicts, okay? You get the predicted thing, which is what you would get if you plugged in basically the parameter 16.85, and this for the linear component and this for the intercept. If you plug those in, you get this and you'd get this, but it also puts in standard error values and creates a confidence interval for the upper bound and the lower bound for kind of your what is it predicting here. Okay, upper bound and lower bound for the mean, and then upper bound and lower bound for the prediction. So the upper bound and lower bound for the prediction is even farther, much more spread, versus like for the mean value, it says, I'm confident that the true value is somewhere between these two things. And to that end, it is correct because the true value was 10, and as far as the getting the true value within the upper and lower bounds for the mean, it did get it. True value is 10, and it is between these things. Okay, so we can kind of take our prediction interval and just kind of take the column of prediction intervals, and then I'm going to just create a plot with everything all put together here. And so the true relationship, and again, because there's so much error, the scaling on this is a little bit thrown off here. But the true relationship is this blue line, okay? And then the estimated relationship is the dotted line, okay? And so for the dotted line, it's a little bit off. And so kind of the important thing was the quadratic component, I guess. And the linear component, which kind of, if you think about in a equation for parabola, changing the linear component takes your kind of your parabola and just slides it over to the left or to the right a little bit, okay? And the quadratic component kind of changes how steep or wide the parabola opens up, okay? So our estimate for the quadratic component is a little bit high, 2.2 versus 2.0. So our parabola, is a little bit steeper, and then its left-right adjustment is a little bit off from the true relationship, okay? But you can see, it's not doing a bad job, because as far as the actual noise goes, we had quite a bit of noise, so the values are just kind of all over the place. So we can understand how the values are generated around the true line. The fitted line is this dotted thing, okay? And then the red dotted lines on the up and bottom is basically the upper and lower bounds for where the predicted values could be. And what we see is that almost all of the data falls within here. If instead of taking the observed CI upper and lower, and if I did mean CI upper and lower, this is going to form a much tighter range, okay? And this is about these bounds, these dotted line boundaries, is the blue line. We're 95% confident that the blue line representing the true relationship is between the upper and lower bounds of this, okay? And as far as our model goes, it got it right, okay? So we're based on the data, we are 95% confident that the blue line, which represents the true relationship, is within the upper and lower bounds here. That's what the mean CI upper and lower. And then as far as OBS, I am 95% confident that random observations are going to be within the upper and lower bounds. And it looks like it got it mostly right. And we have 1, 2, that one looks like it's inside maybe 3 points. 3 points that fall outside of the span here, which is in line with kind of a 95% confidence interval. I think we would have expected around 5 to have fallen outside that range, and we got about 3 points that fall outside that range. So this is mostly correct here. Okay, and that's just a very, very, very brief introduction as far as stats models go. Again, this class is not your 101A linear regression course. It's not a NOVA course either, or things like that. So we can't really get into it too much, but I just wanted to kind of introduce and say, like, these things can be done on Python, and probably the package that you would use will be stats models. Let me give you your third view quiz answer. Question 3 is E, and that is our third view quiz answer. That said, so you can do quite a bit with Python and stats models. Stats models is a very robust package, does quite a bit. Perhaps just my bias of just having used R for quite a bit for linear regression stuff, I'm probably more comfortable using R for doing regular old linear regression model fitting and stuff like that. But yeah, certainly, if you want to do it in Python, it is possible. I frequently have to look up a lot of documentation when I do use stats models, though, just because I'm less familiar with it. Scikit-learn does a lot of kind of machine learning stuff, and I'll just introduce just a little bit of it on Wednesday. So we'll look at scikit-learn on Wednesday, but that will be it for now. All right, we'll go ahead and wrap up here. Have a great rest of your day, and we'll see you Wednesday.